Good afternoon, everybody, and welcome to another presentation by the K-Core Group. We've got Raymond Desjardins as the guest speaker today. And as I was doing a little bit of research on his background, I was overwhelmed by his experience and long employment in the field that he's going to be talking about. Raymond has a BSc in physics, an MSc in meteorology, and a PhD in agronomy. His expertise has ranged from quantifying greenhouse gas emissions, calculating carbon footprints of agricultural products, identifying and instituting reductions of agricultural impacts on the environment. And what we're going to be treated with in this presentation is sort of a review of 70 years of research done in agricultural meteorological work in Canada at the Agricultural and Agri-Foods Canada. So without any more from me, over to you, Raymond, and I'm looking forward to this.
Thank you very much, Phil. Hi to everyone. I'm very pleased to have a chance to talk about what has been done as far as the evolution of agricultural meteorology and focusing more on what we've done in agricultural meteorology to try to mitigate greenhouse gas emission. So today I'll cover a bit of the history of agrometeorology in Canada, a fairly short history, and then go toward measurement of mass and energy exchange over North America terrestrial ecosystem, present some measurement and estimate of greenhouse gas emission from agricultural sources, estimate of carbon footprint of agricultural product, discuss the impact of agriculture on climate, and present some potential natural climate solution for agroecosystem. So the history of agrometeorology in Canada basically started at the experimental farm. The experimental farm was started in 1886, and it's in Ottawa here. And you see Carling Avenue and office where I work, and there's there's a museum, agriculture, a nice museum. It's nice to visit, and there's a weather station around here, and later on you'll see some pictures of the weather station. So it really agrometeorology in Canada started with George Robertson in 1951. Canadian Met Service realized that agriculture were doing a lot of relevant work, but they did not have any meteorologists. So they seconded George Robertson to come and work for agriculture, and they paid his salary from 1951 to 1969. And George, at the time, Met Service had a surplus of meteorologists, so they did that to a few sectors in agriculture. They paid for an agrometeorologist to work there, and they paid for meteorologists to work in the Forest Service. And so George started a program on crop weather development. He started a project investigating the growth and development of the main crop in relation to the meteorological environment for 8 locations. And I'll show a bit of that data because it was excellent data to do agrometeorology. He wrote a very nice paper on the biomet timescale for cereal crop involving day and night temperature and photoperiod, just based on the day length, that's the photoperiod, and day and night temperature. He was able to predict the stage of development of a development model that gave the stage of development of the wheat crop. And a nice summary of the history of agrometeorology. He wrote that in 1989, and it's accessible. It's on the internet, and it's a much better history than I will have a chance to present today, since I'm focusing more on mitigating greenhouse gas emission. So in 1961-62, the Met Service also seconded me to work in agriculture. I was doing a bachelor in physics at the University of Ottawa, and here I am at the weather station that I mentioned before, testing some instrument to measure evaporation. And it started a long career because as soon as I finished my physics degree at Ottawa University, the Met Service hired me to train me as a meteorologist, and I went to Toronto for 2 years to be trained as a meteorologist. And as soon as I finished that course, I was invited by Agricultural Canada to come and work permanently with it where I had worked as a summer student. So it was a very nice occasion. And I arrived in 65, and here was the situation. Agriculture Canada, agriculture had about 64 million hectares of farmland, and 40 million were intensively cultivated. And as you can see, all the crops were certain regions specialized on certain crop, and it's pretty much still the same. There's been some change. For example, now there are a lot more canola grown than wheat. In those days, there were much more canola grown than wheat, and I will talk about that a little bit. But basically, like in Ontario, for example, grain, oilseed, and dairy is a big thing, and in Quebec, hog production, and in Manitoba, hog production is also a big part of the farming. So as I arrived in 65, I went to Cornell to do a PhD for a couple of years, but for 3 years, and I will discuss a lot of the type of research that we did, which is quite relevant to mitigating climate change. But before that, though, I'll summarize some of the projects that were being done in agrometeorology. For example, here we developed with the data that George Robertson had collected. He had collected data at six locations in Canada, and he had all the yield data. He had the phenological stages. The phenological stages, that's planting to emergence, emergence to jointing, jointing to heading, heading to soft dough, and soft dough to ripe. And this is for wheat. And so I wanted to find out what are the critical phases of growth, what affects the yield of crops. So I took 10 years of that data, and I took the 5 best years where the yield were the best, and the 5 worst years, and look at this, how many variable as showed a significant difference between the good and the bad year. And right away, for example, we see station up north at Village, Fort Vermilion, which we were talking about a few minutes ago. They had early frost, and the yield was very affected by that. While other location like Ottawa, this was not affected at all, very much. And but Ottawa, things like dry period during the summer, during jointing netting, affected the most the yield. So it gave us a bit of an idea what are the critical phases of growth. And I am afraid to say that we should do that for every 10 years, and we would find big difference from year to year. And it would be very interesting to do. So I try to encourage students to do a little project like this, because as you see here, it shows the mean temperature pre-industrial period, and it shows the temperature on a daily basis, January to February to December, and as the mean temperature, global temperature, and as it increased over time. And these dark blue ones is around the 1940s, and then 1960, 1970, 1980, and this was the last year, for example. And you can see that the temperature was beyond anything that we've experienced almost, and here we're talking of only 1.5 degrees centigrade, and people sort of think, what's 1.5 degrees? That's nothing, you know. But I always try to use the analogy that if you have a fever of 1.5 degrees, which is about 100.5, you don't feel very good. And if you had a fever of 3 degrees, you're quite sick. And you know, and I'm surprised that analogy holds true, but it seems to hold true, and it's something that one should try to find out why that resemblance a bit more. So. Even so, the initial studies were not very, but even the more recent studies, like one of my colleagues, Ward Smith, wrote a paper assessing the effect of climate change on crop production in 2013, and he predicted a huge increase. He used the climate scenarios, IPCC climate scenario, where he predicted increases in yields, for example, of wheat, winter wheat of 30 to 40% by 2040 to 2069, based on the fact that the carbon dioxide concentration is increasing and the temperature, the length is long, the growing period is longer. But more recently, some people have written series of publication where they show that temperature over 32.8 degrees Celsius affect the enzyme in plants, and in wheat the enzymes start to break down. These enzymes convert the carbohydrate to the CO2 to carbohydrates in the plant. And some of the recent publication mentioned that 1 year out of 6 we can expect some major decrease in yield of crops like this. So, and a more recent publication, one of my colleagues, Sam Carabado, and we wrote a paper on an indicator of killing the fruit trees during flower race. Because of the warm spring, fruit trees flower earlier, but sometimes there's a front pass which had caused damages, frost damages, and the repeat period of that occurring is becoming more and more frequent. So today, though, the most of the focus will be on research that we've done in the last since 65 to 2023 on what could we do to help mitigate climate change. So one of the first things I'll talk about is measurement that we've done, measured an estimated mass energy exchange associated with some of the major ecosystem in North America. And it's quite important because agriculture is only 7% of the ecosystem in Canada. And we have 1 billion hectares of terrestrial ecosystem, and we represent only 7% of the. So it's important to look at the other ecosystem, and we'll talk about that. Then we'll show measurement and estimated of greenhouse gas emission associated with the agriculture sector and other sectors, and present some estimate of the carbon footprint of most agricultural product and the difference in radiative forcing. Radiative forcing is factors that affect climate change associated with several management practices, and our recent estimate of quantify the impact of agriculture on climate and identify ways to reduce it. So as part of my PhD thesis, I went to Cornell, and I spent 2 years before going to do my PhD, before asking Agricultural Canada to send me to do a PhD. And during that time, I looked at a lot of things there, and they were crop growth was just measured by measuring the weight of the crop on a monthly basis. And I looked around a little bit, and there was a group at Cornell that was measuring CO2 flux using a gradient technique. They measured the carbon dioxide concentration and water vapor at 10 level above and in the crop, and then with the wind condition measurement, they estimated the flux. But someone was using a technique called the eddy correlation technique to measure evaporation using measurement, like measuring vertical wind with an instrument like this. The propeller turns one way when it's in updraft, another way when it's downdraft, and they were measuring water vapor. So I modified an infrared CO2 analyzer, commercial instrument, and passed the air through very fast, and increased the response time in a matter of at least half a second. It could measure anything as far as CO2 fluctuation. So we started to measure, and knowing that 1.5 gram of CO2 absorbed produce 1 gram of dry plant matter, we could measure the rate of growth of the crop in matter of minutes rather than months. And this was a very exciting period. And later on, the instrument got even more sophisticated, where we had open path analyzers to measure CO2, water vapor, and then we had sonic anemometer to measure vertical wind. And now this technique is used all over the world there are thousands of systems measuring CO2 and all gas exchange. So I'll say that's the only equation that I will show a little bit. That's how the flux measurement are done by the covariance technique. We have an instrument that measures, this is time or distance here, and it measures the fluctuation of vertical wind is in black, and the fluctuation of a scalar. Like here, I show the fluctuation of water vapor, but it could be the fluctuation of CO2 or any instrument that responds rapidly. And as you see, when the like for when the vertical wind is positive, like zero is here. For example, the water vapor conservation is larger. When the vertical wind is negative, downwind, water vapor conservation is less. For CO2, it's just the opposite. So and to calculate the emission, you just have to, you have a scalar X and you have a mean for the period that you're working with. And for measuring the flux with a tower, for example, the mean is half an hour. And the X prime is the deviation of the scalar, like water vapor, for example, or W prime. And to get the flux, you just have to get the mean of the fluctuation of W and water vapor, or W and CO2, vertical wind CO2, and usually the vertical wind is equal to 0. So this epic covariance technique is a useful tool because it permits to quantify fluxes for an entire ecosystem without disturbing it. It's based on the assumption of that stationary and emergent. And you can replace time with distance. And with this idea, then we went and did the same thing with an aircraft, with the Flight Research Lab, and Ian McPherson had already given a little talk he was doing on using this aircraft to measure evaporation over a lake. And he went to give a talk, and after that I met him at the meeting, and I said, you know, I just developed an open path CO2 analyzer. My engineer in Agricultural Canada built that for me. So he got it installed in the plane, and we started. And here, for example, you see CO2 now, because when the air goes up, the concentration is less because it has been removed from the crop. The crop has removed. So you do this calculation, you can calculate the rate of growth of crop and kilogram of CO2 per hectare per hour, and any kind of, and since to get the actual value, you have to pass a few times, or else fly along this to get the mean, because air goes up and down, and it's the way. And this is at the time the tower-based system that we had. And so we made the cover of Science in 1982, and that was a very exciting time because I never did it after or before. So when one has an idea, one doesn't realize how it is at the time. And so we should not belittle things that we do at a certain point. You know, like there are many other times I should have done the same thing, but I didn't do it. So, so here it shows the Flight Research Lab, the Twin Otter instrumented, and it's been a wonderful experience. I've worked a lot with Peter Schrepp and Ian McPherson, putting sensors on. We put all kinds of sensors to measure the flux of ozone, the flux of CO2, the flux of water vapor, and all kinds of satellite simulators. To here we measure the vertical wind. So we're able to correct and get vertical wind very accurately, and just like on a tower, it's a moving platform, but we're able to measure the flux very, very accurately. And we have satellite simulators, which the idea, and I think we have hardly done with that, is to develop with this data to develop environmental response function that can be used to improve the value of the satellite data being collected worldwide. You know, and it has tremendous potential. We even developed a new technique called the eddy accumulation technique, which it shows this allowed us to measure the flux rather than having a fast response analyzer. Sometimes they don't exist. Like for one time, it didn't exist for nitrous oxide. agrochemical, volatile organic compound. So this, we collected the air. When the vertical went up, we would collect it in one reservoir, and when the vertical wind went down in another reservoir, and at the end of 10 kilometers, for example, we would have two reservoirs or two bags, and then put some other bags, and then go back to the lab and measure the change in concentration in these bags, and we could accurately measure the flux of all series of chemicals. And one, for example, that this I won't say much on this today, but I should mention, like, one example that we did is measure the flux of VOC, volatile organic compound, and these are given by trees, for example, isoprene and terpene, and these compound bind the hydroxyl radical OH, and these hydroxyl radical, we rely on these they control the half-life of methane in the air. So we really don't want too many of those, because if these VOC bind the hydroxyl radical, they're not effective to remove the methane. So the methane life in the atmosphere can change because of that. So the shorter the methane life in the atmosphere, the better it is. So there are little things like this that we learn over the years. Like so having developed this system, it was quite and our NASA was very excited about this, and they invited us to participate in many field campaigns. And I'll go through a couple of these campaigns. And one thing that I put a reference here, in 2016, I wrote a summary with my colleague of all the data that we collected. And like I said, there's billions of data points, and Devin worked at Agricultural Canada as this whole data set. And we've been very lucky to have many postdocs who have come and taken some of this data to do all kinds of analysis, which I won't talk about them today because it's too much. Sometimes they're not related to mitigating climate change, but they were very exciting to understand ecosystem functioning and all this. So today I will talk about the 5.1 bit and the Boreas experiment and the northern wetland, and that's about it. But we have data, enormous amount of data. Like we measured the ozone deposition, absorption of ozone in California. In this one, I will not show it either, but we flew over the city of Fresno and measured the CO2 from a city. People want to know how green their city is. This would be a very, very good way to do it. So okay, 5 was the first international satellite land surface climatology project field experiment, and Pierre Sellers was in charge of that, and they paid us to go and study the Kanza prairies, an area of 15 by 15 kilometers, and the idea they were using satellites to see how this respond, and we had all kinds of tower-based system over to study different parts, and the next slide shows, for example, people were measuring plant response, people were measuring a tower, we were measuring with our flux aircraft here, and a lot of spectral data was being collected also over the site. And for example, we flew a grid pattern at 100 meters above the ground, and we measured the CO2 flux here. This was superimposed on a Russian satellite, which measured I showed the ratio of infrared radiation over red over infrared, and red means lots of green vegetation, and this more intense the red is, more green, less intense is less green, and you can see it corresponds very well. The flux of CO2 in kilogram per hectare per hour is bigger over the red section and all this, and people, they had towers in a few places. There was a little problem here at the time, which was not there, and we had to learn to use the system, and there was a big gully here, so I won't talk more about that, but we are also able to measure evaporation, and if you want to come, I put it in millimeter per day, but if convert it to watt per meter square, you have to multiply by 25, I think. Yeah. Okay, so we flew this many time, and as you can see, it's in Kansas. There's ready. It's complex system, but it integrated the area very well. So we went to other parts of the other field campaign, like 1990, studied the Hudson Bay lowland, Environment Canada at a tower there to measure, and it's quite a complex ecosystem, the Hudson Bay lowland, and we were going to mainly to measure methane, but at the time the methane analyzer did not work, so we measured CO2, and the next slide showed that something quite interesting. Like one day, Ian, on different days in the year, Ian McPherson had selected 3 regions. We would fly 80 kilometers at 30-meter high over the northern on different days, and here it shows the temperature on all these days, and the other one is region 1, region 2, or region 3, and what basically it showed, what we later on learned, temperature controls. These wetlands are controlled by temperature enormously, and even the border forest, for example, would not grow past 26, 27 degrees C. The plant closed their stomates, and we observed that a lot, and it has a lot of implication with climate change in a way that as temperature gets higher, temperature will have a lot of effect. Normally, in agricultural crop, temperature does not have that much effect. It's much more radiation. But here, temperature has a dominant effect in those type of ecosystem on CO2 exchange. Another big project that we did was over the boreal forest. We work a lot with the Environment Canada for the Sea Continent Center for Remote Sensing. Joe Lara was very involved with that, but it was mainly inspired by NASA with a lot of Canadian cooperation. And what they did there, they selected two 15-kilometer area, 15 by 15 kilometer area, one in the southern area near Prince Albert, and one near northern area near Thompson, Manitoba. They set up towers at all these places. For example, in southern area, they had towers over black spruce, over jack pine, over aspen, over fen, and they would fly this. We would fly the grid pattern at the same time as the tower people were measuring the fluxes. And we'll next slide try to show how one of the things we learn a lot is the footprint of a measurement. For example, like under tower has a very small footprint, and depending on if you have very hot unstable condition, the footprint is very short. Under neutral condition, it's longer, and same for the airplane. But the airplane has a much larger footprint, because the higher we are located, the larger the footprint too. So usually we flew these at around 100 meters rather than initially when we started our work, we were flying at 5, 10, and 25 meters, and but at those level, even then our instrument were not responding fast enough to get all the fluctuations, so we underestimated the flux. So, but at 100 meters, with all the instruments we have, we were able to get very good flux estimate. So we flew a grid again, a grid pattern like I showed you for the grassland in Kansas, and we knew how much we used the area of the that these towers represented, and combined this with we did not have any measurement for lake, but the emission would be very small and rock would be very small. So we came up with estimated and measured with the airplane, and estimated using the tower measurement, and it went pretty well. We still have a few things to improve, but it was quite good. The comparison was very good, and so now thinking about quantifying agricultural greenhouse gas emission. Here are all the tools that we've used. Philippe Rochette was very involved. He joined our group and started the chamber type measurements and did a lot of work on these that I will show around a little bit. It's the measurement that is probably the most, we have the most, but it represents the least area, but it's very good for analyzing the impact of different treatment. You just put a little cover over a small surface and you can measure the CO2 uptake, you can measure the methane uptake and nitrous oxide emission. And these are the three main gases that we are interested in agriculture. Andy van der Zag and his team now do these, I'll show more of those. We set these, it's a laser and reflector about 100 meters away, and it measures the concentration in that path length. So you measure you put that downwind of a manure tank or over a lagoon, and you're able to measure the emissions of ammonia, methane, and carbon dioxide. The tower-based measurement, and you see the scale that these measurements cover. No measurement cover the whole scale, so it's important to combine. Like a tower-based measurement can be used for almost a year at one place, but it covers a footprint fairly small. Another one is a balloon, which I will show. You take some profile of the gas at night, and I'll show you that. And an airplane is another one that we've used a lot. And you need model and satellite data to have the complete picture. So it requires a full team effort. So, and what we're trying to measure is the methane absorption by soil, methane emission from livestock or manure, N2O emission from manure, N2O emission from crop management, CO2 uptake by plants, CO2 emitted by soil and other sources. So here's the chamber measurement. Like I said before, they're the most commonly used technique to measure greenhouse gas emission. And Philippe Rochette has many papers when to use them and all this. And more recently, Dan Pennock used many chambers, and we flew over the area and compare the emission from the chamber, integrating the chamber to our aircraft flux measurement of nitrous oxide. And the agreement was pretty good, but the chambers, you could see they measured the emissions sooner than we did, because the chamber affected warmed the soil a bit more, and but the total was pretty good agreement. So the system that is being used a lot now on farm is methane emission. It's Andy van der Zag and MBLU have a system to when they measure the methane. They have the laser to send the beam, and they measure upwind and downwind. And there's a package called Thunder Wind Tracks that does once you know the wind condition with a sonic anemometer, you're able to calculate the methane emission quite well. And here's an example. We went downwind of a feedlot in Edmonton, and we measured the methane emission from livestock. And this is the mean methane emission per animal per hour. And when they eat in the morning and at night, the emission are mainly from enteric fermentation, which is in their rumen, the bacteria break down the carbohydrate that they have eaten, and they release methane there. And what was interesting in this is the emission factor. Like YM is a methane conversion factor, which is how much methane per gross energy intake that an animal eat. And over a feedlot, the quality of the feed is so good that the methane, they would YM was 3, while if over pasture, if the pasture is poor, it can be 10, 12. You have to be 4 times more to get the same effect, you know, like this equation is used a lot for calculating methane emission inventory and all this. So here's the technique that could be used over cities. For example, Elizabeth Patty has done this work over agricultural region. At night, we have inversion layer where it's like a cover. It's like a cover over the region, and the gas cannot escape. And so, if you measure at, for example, the mirror measure at almost 2100 and almost at 2300, from 21 is 9 o'clock to about 11 o'clock, and the nitrous oxide concentration changed that much. So with the difference in change in concentration, you can calculate the emission. And I flew with the airplane in Kansas and all this, and I showed that at a certain above the inversion layer, at night there are no emission at all of the gas coming out from the surface, because the inversion layer stops everything. And this is quite an interesting aspect. I would think that the balloon should be used like this over city to decide how green the city, and we wouldn't get the reaction that we got from the FAA when we flew at 100 meters over the Fresno to get the measure the emissions in the city. So here we're looking at the with Environment Canada and Agriculture Canada, we generate methane emission inventories, and we thought we would try to go and verify these inventories. Like, in the next slide, we because of the dairy quota, we know exactly. We knew Dairy Farmers Canada told us exactly how many animals, dairy cows they had in Eastern Ontario. It's very confidential. As long as they don't show the detail, they said I can show the result, but not much detail. So we knew exactly where all the animals were, because the animals are all indoor almost in dairy production, and how many we could calculate the emission of methane for the inventory, and go and verify. And we did that on many different occasions. The wind in this case was coming. I'll just show one that transect there. It's 20 kilometers long, and the wind's coming like this. We're flying at 100 meters above the surface, and we measure the methane emission. And here, for example, first you have to realize that here's the transect that I just showing. The wind is coming from here in this case there. So the footprint, you don't get much contribution to the flux there, but the closer you get to the line you are, and depending on the height of you are, Peter Schwepp had developed a excellent footprint model that we were able to integrate all the emission and from this, and come up with a flux value for the methane that the airplane measured. And when you look in this case here, for example, our inventory underestimated. This dotted line is the inventory estimate, underestimated, because here there were a lot of wetland. There was a bit of wetland here, so the airplane measured everything, not just the emission from the farm. So we end up, but it was a help increase the confidence in the inventory that estimate that are generated. So here is another example of there are other sources of many important point sources. And between Ottawa and Montreal, there was a La Flèche place waste treatment site, and we decided to go investigate it and measure the methane emission from it. And here we showed that the methane emission were 2,000, about over 2,000 kilograms of methane per hour from that waste treatment site there. And this is equivalent to 100,000 dairy cows. None of these emission are counted normally. You know, there are many. Recently, Professor Carlton reported that methane emission escaping Alberta oil well are reported to be 50% underestimated. You know, and Tom Flesch did a lot of work. Like we're very promoting biodigesters, that type of thing, but sometimes the farmers are not quite informed. At first, you have to do flaring, you have to do all, we have many interesting data downwind of these biodigesters, you know, like if they're done properly, if they're done properly, it's good, but there are many sources of methane that are sometimes underestimated. So we thought we'd go and verify other inventory like nitrous oxide. Nitrous oxide accounts for about 6% of the agricultural emission of the Canada greenhouse gas emission, but most of over 60% of these come from agriculture. So we took flew two transect in Eastern Ontario near Castlemaine, and we this could make David Pelster, for example, is doing some work right now verifying inventory of N2O emission. It'd be a fantastic data set to come up to verify how well we model these emissions, you know, like because it's one chamber in here would be a bit tricky because it's such a different large variation. But we did some flight near Castle in the spring of, I think 2000 or 2001, and we did these two transect. There are large emission of nitrous oxide associated with spring bursts, like just when the soil became unfrozen, and we flew at these two places, and it was remarkable the agreement from two places, remembering that how we collect the data, and this is no emission for a while, and I was quite pleased the agreement that we had from this, and so we did that for 4 years, and the modelers, Ward Smith uses model to predict this, and and we measured with the airplane, and you know the airplane, I think most of the time was a bit larger than the model, but probably needs a bit of an adjustment for the model, but there are many indirect sources which are difficult to account for, like ditches and all that type of thing. But so here's one of the model, because we cannot measure everywhere, so it's important to use process-based model for. And Ward Smith has done a lot of work with Brian Grant to use the NDC model across to come up with the N2O, methane, and soil emissions at the farm level and all this, and it's quite complex, and Jiansheng Li had developed this model. I think he's dead now, died, but he from Penn State, and this model is being used worldwide to estimate emission. So here's an example, but we ran it for several years. He ran it for several years, and this is the spring burst part, and this is the total emission, I think, for Canada. So in Canada, from 1978 to 1999, you know, so it's that kind of thing. On average, Canada spring emission these spring represent about 30% of the emission, and that's a very, so here's the different model to estimate the carbon footprint and the greenhouse gas emission. They send the NDC manures used. Ulysses is United Livestock Industry Crop Emission Estimation System by Xavier Verger, a postdoc and a scientist with us for many years, developed that. Roland Krobel now as a OLUS is a new version that is accessible for farmers. It's a greenhouse calculator that farmers can use to estimate their own farm emission. I'll say a few more about this. Carbon CF, this is carbon footprint of Canadian food. Was developed by Dominique Maxime de CIREG in Montreal, and F4E2 is one on-off farm fuel emission. This, I won't go into too much detail, but Jim Dyer has been developed this, and it's quite interesting because these emissions are not counted in the agriculture emission normally because they're reported by the transportation, the industry sector, and all this. But if we want to calculate the carbon footprint of agricultural food, we better have this estimate. So with his model now, he's able to come up with a very good estimate of this. And here, the emission that from agriculture, fossil fuel emission are about 26% of the Canadian agricultural emission, and they're not counted in our inventory because they count by other people. And methane is mainly enteric fermentation and a bit of manure. Nitrous oxide is direct from soil, manure management, and indirect, like emission from ditches, that type of thing, where fertilizer runoff and this. So it's hard to force, but unless you have an integrating system like the balloon system or the aircraft, or you cannot measure these completely. But this is the field work is very important for the CO2 emission. So if we'll next talk about the carbon footprint of food, we need to take all these emissions into account. And here's an example that Jim Dyer calculated for by ton of CO2 equivalent per hectare, or ton of CO2 per ton of dry matter. CO2 equivalent includes methane and nitrous oxide. Like you calculate this over a 100 period or 20-year period, and methane is more potent than greenhouse gas, so you weigh that into account, and nitrous oxide is even more potent than CO2. I mean, and so. This is interesting because crops that produce a lot, like not by ton per hectare, when you ton by ton of dry matter, the emission not as large because they're very productive too. So this is what it says. On an annual basis, crops that are ever fertilized, like corn, tend to have a high carbon footprint, whereas crop that fix nitrogen and are not fertilizer, soybean and alfalfa tend to have a small carbon footprint, but on a dry matter basis, it's quite a bit different, you know. So I won't spend the time burning out on that, but just to show that the carbon footprint of crops can vary enormously across the country by province, because it depends a lot on the precipitation, the moisture in the soil, many other factors, and also the practice that are done in the provinces. So you can see, for example, potatoes in the Atlantic province produce more ton of greenhouse gas per ton because it's quite wet, but that's where they're grown the same because, you know, like the presentation will be available online after, and people who are interested can go and look at that. So for an example of the carbon footprint of how to calculate dairy production, you have to figure out the dairy population, the feed ration they have, the crop complex. I'll say more about that, what they eat based on that, and we calculate the carbon footprint of the food that they eat, and we have to count the methane emission from the livestock, and nitrous oxide and CO2 emitted. We have to go through all this process, synthetic fertilizer used to come up with a carbon footprint. And here's the crop for dairy production, for example. We have here the feed ration of the animal, and we calculate the amount of greenhouse gas to produce these feed, and come up with carbon footprint per kilogram of product. For example, for all the dairy industry, like cheese, milk powder, for example. It takes a lot. Fluid milk, for example, it's about one there, and you can compare with other countries, that kind of thing. But for example, if you make milk powder, it would take, that's a kilogram of CO2 equivalent per kilogram of of milk powder. It would take a lot of milk to make milk powder. So it's quite a range, but it's useful information. So here's the greenhouse gas calculator that Roland Probel is working on these days to help farmer make decision about how they could reduce their own farm emission, because there's a lot of management practices they could do. And the Living Lab is working with that quite a bit to help farmers make decision to reduce their own farm emission. And a lot of the carbon footprint work that we're doing is also to help consumers reduce their greenhouse gas emission. So I won't go into more detail, except that we try to count everything: the soil organic matter, the imports to like fertilizer, everything's counted as much as we can, nutrient applied into emission. So there are numerous agricultural practices that result in less greenhouse gas and an increase in soil carbon sequestration. This is what most people always, we talk about soil carbon sequestration all the time. Today, we'll try to talk about something else too, but use of biodigester is one, because you go put the manure directly in, and it's a planting windbreak is very common out west too. You store carbon in the trees here, but reduced tillage is probably one of the biggest one, where farmers used to cultivate their field enormously. Now they can plant with minimum tillage. They use herbicides sometimes to kill the weeds, and all kinds of new techniques that makes that you lose a lot less carbon that was sequestered in soil. And now the good practices, we're putting back carbon in the soil. One big thing is we used to have 13 million hectares of summer fallow. It means that every second year or every third year, farmers would not plant crops and to conserve moisture. And so because these things started in the Great Depression, I guess. And so, but now there used to be about 13 million hectares on reduction of under summer fallow. Now at the most is 1 million hectares, even less nowadays. So more digestible feed ration reduced, like I mentioned before, the feed loss, for example. But good forage crop is also very good. Like a feedlot is very good, but there are other problems too. So planting perennial crop is one. So I'll go through some of these, and here I show we've calculated with Brian McConkie. I've done a lot of work on that, calculating the soil carbon change. Like we use the soil carbon is increasing with time, and now I started because of this change in management practice, like reduced tillage is this one, reduced summer fallow, reduction of reduced summer fallow is a big one, and change the mixture, more perennial crop. So now the benefits are starting to decrease, but we're still storing a lot of carbon in our soil because of these practices. So comparing the emission intensity from agricultural product is quite complex though, because it's not fair to they're functionally different. So however, one primary factor is to provide protein for growth. Therefore, especially the carbon footprint per unit of protein is one way to compare the greenhouse gas emission. So my colleague and I have written several papers on that, and we've come up with the greenhouse gas emission in kilogram of CO2 equivalent per year per kilogram of protein. And lamb has the worst record there, and beef is the next one. Milk, poultry is 10 times less than beef. Pork is 5 times less than beef. So later on, I will talk about some scenarios that we have to reduce the emission there. So I'll go fast. Here's an example of plants also in the mix. Like And first I should share ruminant, for example. We have to allocate the emission ton of CO2 per ton of protein for beef in the West is more than the East, not because the East are doing something better, except that half of the beef come from the dairy sector. So we've already allocated some of the emission to produce the milk, you know. So so you have to be fair and not count all the emission, because these are all agro-ecosystem, are complete system. So non-ruminant is not quite as much, like that. Pigs are in that, hogs are in that category, and chicken and all this. And soybean, for example, the emission from soybean, you get almost the same important protein from soybean, and it produces 200 times less greenhouse gas emission per kilogram of protein than you produce eating beef or lamb. So this is quite important thing to consider. So pulse and soybean present a far less carbon-intensive method of producing protein as compared to ruminant and non-ruminant. For example, the amount of feed input for ruminant equals 15 to 30 times the mass of the final meat product. So we've generated something recently with Jim Dyer and I and Devin Moore and a few people. We look at trying to see, in Canada we consume a certain amount of protein. If we were going to try to, what could we do to reduce, the consumer could do to reduce its emission? For example, right now, if they reduce their emission of meat, by the consumption of meat consumer by 24%, for example, 25%, they would reduce their emission by 4 million tons. And if right now in red meat, we eat 50% pork, 50% beef. And if we were going to say, okay, we'll have the same meat, but we'll eat 70% pork and 25% beef, we would reduce the emission of the agricultural sector by 9 million tons of CO2 per year. Remembering that agricultural emissions are 60 million tons, it's already Jim Dyer and I have made a little video, which I won't show you now, but you can look at it after. It's a 3-minute video. We're trying to convince consumers what they could do to reduce their methane emission and help the agricultural sector reduce its emission. So another little thing, I'm almost finished here, but is people always say buy locally, which is true, but I am very much in favor of that. But I thought I would show this slide. Well, my colleague Jim Dyer has done a lot of work on whether because of what to do to reduce your greenhouse gas emission a little bit is suppose you import your vegetable from Florida, for example, from here, the emission of greenhouse gas emission from these numbers are larger because we produce more in Ontario vegetable than in Quebec. Import your vegetable from Florida, or out west, import your vegetable from California during the winter. If you import them with truck, you still produce more by trying to grow them in Ontario. And the same thing in Quebec, you still produce a bit more. And if you import them by airplane, you better grow them in your greenhouses rather than, because then you produce a lot more greenhouse. It's sort of a nice, cute little example. So now trying to quantify the impact of agro-system on climate. This is the part that is not being done very well. Biogeochemical is the carbon sequestration and all this greenhouse gas. Biophysical is other factors like albedo, reflectivity, like I've talked about before. Reflect your radiation, either reflect radiation or use it to absorb carbon. But so there's some benefit there that our agro-ecosystem could help minimize climate change. So in a short, what causes climate radiative forcing? Radiative forcing or climate forcing is the change in the energy flux in the atmosphere measured in watt per square meter caused by either natural or anthropogenic greenhouse gas. Anthropogenic, like producing fossil fuel, the time greenhouse gas like this, I think, and extra forcing 1 watt per meter square on a global scale is produce a mean temperature increase of 0.5 degree C. There's a bit less than that because there's warming, the oceans are warming too, so it's not quite that, but as far as energy, so Alan Betts and Alan Betts generated this a few years ago, the whole energy budget, and I see the time. I don't have to spend much time, but on it, but it's important to reflect your radiation. This does not have any effect at all, and this is what the rest of the talk will be about. Changing this has a lot of impact on mitigating climate change, and it's not being counted at all right now. And if the rest of the energy goes in long wave and that absorbed by greenhouse gases, and that's how part of the climate change issue. So to slick the impact of management practices, they have a biophysical, geophysical effect and a biogeochemical effect. And I will talk about this, like some of the reduced tillage. I've already talked about afforestation, deforestation, biochar, putting biochar in the soil, store carbon, which is good, but change the reflectivity of the soil a bit, and it might absorb more radiation. A lot of these we have not calculated. The reduced summer fallow, for example, it's good both ways. Reduced summer fallow, now you have more crops, so it reflects the radiation. Summer fallow was bare soil most of the time, so the albedo, the reflectivity of bare soil is not very good, so it absorbs radiation, and biogeochemical, you store carbon because you reduce. So crops, cover crops. I'll say a few more about all these things very rapidly in a few minutes. Sorry, I put so many slides. So here's a very interesting one, though, that became as a shock to Alan Betts and I when we measured the net radiation over the boreal forests, and we measured it over a deciduous forest like aspen with lost its leaves, and over grassland. And there was a huge difference in net radiation, especially when there's snow on the ground. These things that I'm talking about with the forest being not that great planning doesn't apply at all in South America and where there's no snow. It's more with coniferous forest, for example, which is this, hides the snow, and so the net radiation difference was 14 watt per meter square, which is enormous. When people realize that, it's equivalent to 7 degrees C, and this is just so. Alan reports that when the EMCF, the European Community, doing this forecasting, realized that the forest would not be behaving like grassland, they changed the reflectivity of the forest, and it changed their model prediction quite considerably. So, and I didn't realize that, but Alan took every time we were flying over the boreal forest as part of Boreas, we flew over an agricultural region. And so whenever we had we show here the net radiation as a function of shortwave radiation, and the 50 watt per meter square difference. This is because most of our flight now were done at around midday. So like before we were talking about 14 watt and 3 watt. Here at midday, it's a huge difference between forest and grassland. So these are benefits that are not really recognized by agricultural land. So Zhang Liu works with very often. We work together very often. He's in the same center as I am, as I was, and he's just generated this curve recently. I don't want to have time to talk about. He looked at the impact of forestry, and he looked at 2 levels of production: 5 tons of carbon per hectare per year, or 2 tons of carbon per hectare per year. And here he looked at the low productive forests, productive forests that produce 2 tons of carbon per hectare per year. The albedo effect here shows the cumulative net effect. So the global warming for boreal forest, for Peace River forest, and then Peaceland, Aspen Parkland, and the reinforcing due to albedo cause warming, and the sequestration, the carbon sequestration cause cooling, and it takes a long for low production forest takes a long time. For highly productive forests, it happens quite more rapidly, about within 30 years of planting, and then it cools off, cause cooling. So and to support this further, Pierre Bernier, who works in forestry, wrote a paper a few years ago where he showed that after a series of forest fire in eastern Canada, it was lichens form on the soil, and it takes forever to get planting forests. Takes forever to gain anything by planting forests. It was better not to plant forests, but people already had contracts to plant forests, and so that paper that Pierre wrote was not very popular at the time, but it should be. It's quite serious. So management on biophysical forcing, how to do this, identify. That's the type of thing that Jean-Louis Liu does a lot. Identify field with known crop type and management, estimate annual albedo from satellite imagery, and scale up to national scale. And you see, for example, that's the satellite imagery. There's quite a difference in reflectivities of these crops, like summer fallow, like it reflects very little radiation. Low albedo, high albedo, the albedo is low albedo versus high albedo here. So, this equation can be used to calculate. Therefore, knowing the reinforcing impact of a management practice on albedo, you can calculate the carbon equivalent impact. So, with this equation, and that CO2 uptake required to make this equivalent to albedo effect, and we show you in 2 slides. For example, this slide here, reduced summer fallow. This was the biochemical effect over from 1981 to 2000. The average from 1981 to 2016, and this is the albedo effect in million ton of CO2 per year. So this is not counted at all in Canada yet, but it's more. Most of the effort is on this aspect. So very important to be aware of this and to do the proper counting. And that's what my final word in my conclusion. Another thing that has happened in Canada is that area of wheat has decreased significantly, and now canola has an area of canola, and it's not very hard to see that this crop is highly reflective compared to a canola field versus a wheat field. And so Jean-Louis calculated that recently, and from 1998 to 2020, this is in million ton of CO2 per year, and the amount, million ton, not per year, certainly on this year, not per year, million ton, and this is for reduced tillage, reduced summer fallow, and shifting from wheat to canola. And there are many other factors. All the list that I had before should be in this and should be counted, and it's not. So in the final section is pathways to reduce GHG emission. A group of science, Nature United, a group with Ronnie Drever, recently got together and invited scientists from Agricultural Canada to make some proposal on how they figured they could do to reduce greenhouse gas emission. most of these are all reducing mainly with increasing carbon sequestration, but they're reduced tillage, cover crop, use of cover crop, legume crop in rotation. Legume crop, you don't have to put as much fertilizer because legume fix the nitrogen from the air, and legume on pasture, silvo pasture nutrient management, avoided conversion of some shelter belt, like because they take the shelter belt, tree intercropping, riparian forest, biochar. Devin Ward and I picked manure management as one of the practices. So they came up with an estimate. These scientists from agriculture came up with an estimate how much they could do in how much greenhouse gas emission equivalent per year by doing certain practices. But there's a cost to this, and convince farmers to do this, we have to convince consumers and farmers of things to do to help the environment. And ours was manure management, which it's involved. There's a lot of uncertainty in all these things, and this is what these arrow and cost that it would cost, how much it would cost to get this. Ours in manure management, for example, it would be to get. It's being done in Denmark. Is to use acid in the manure tank in the spring. After the tank is emptied, put sulfuric acid in the tank, and you reduce your emission for 4 months. You kill all the methanogen bacteria, so there's no methane emission for 3-4 months. Andy van der Zag is doing quite a bit of work on that these days, and in Denmark it's done. It's then done, and last year they invited us to go down, and I should have gone, but I didn't go to try to promote this. So there are a lot of things there that could be done. One thing that Daniel Massé at Lennoxville had done, he had before several years ago to show that he had taken small manure tank and cleaned them completely in the spring after emptying the tank. Farmers cannot do that, but he was working on an experimental farm at Lennoxville, so he cleaned, and there were no emissions for 3-4 months of methane. So the acid is doing exactly the same thing. So there's hope, and here it shows that livestock produce 1.1 million tons of CO2 equivalent per year per animal, and hog produce 0.2 tons. So counting the animal total in Canada, we could reduce the methane emission by 3 million tons of CO2 equivalent per year if we adopted that immediately, and if farmers were given money to have a consultant come to their farm and in the spring spray a bit of sulfuric acid in their tank. And right now they're a bit afraid of doing this, so hopefully Andy van der Zag will be able to demonstrate with Living Lab that this can be done safely. So finally, in conclusion, sorry about that. We've been hopefully I showed you we've done considerable progress in agricultural meteorology in the last 70 years, and the multidisciplinary approach of measuring mass and energy exchange has helped improve our understanding of the biosphere-atmospheric interaction at the ecosystem scale. We made considerable progress in quantifying greenhouse gas emission from a wide range of sources and estimating the carbon footprint. We showed how producers and consumers could help reduce greenhouse gas emission from the agriculture sector, pathways that could reduce agricultural greenhouse for more than what the actual present emission have been identified. Agro-ecosystem represent only 7% of the terrestrial biosphere in Canada, so it's important to be aware of the role of all major ecosystems. And then one very important thing I think is estimates of the radio forcing Saska need to be greatly improved, and we need to improve our counting of these things. Thank you very much. Oh, I should just say a few words. All the fantastic acknowledge all the people that have co-authored and helped me in this type of work. I'm sure I'm missing many, but there are quite a few here that have greatly contributed to this work. Thank you very much.
Okay, well, thank you very much, Raymond. One of the things that I note is that most of the people that are new to viewing our presentations haven't been presenting any questions in the chat box.
Okay.
That is how I determine who is speaking next, is by going down and following the sequence of entry of questions. I have a question that arose very early in your presentation, and it was a parallel relationship in humans and vegetative forms of small temperature increases on bacterial and other microorganisms. And so I was wondering, how serious is that to our crop production, our vegetative growth, all of which we depend upon? When does the ball crash?
Yeah, that's a very good question, Phil. I know that there's been a few papers recently affecting the enzyme in plants, and that's quite serious. They've been predicting 1 year out of 6. I like the analogy of the fever and the earth temperature, and it's probably more real than I realize in a way, no? But I'm not very knowledgeable to say when that will crash. But I think food production will crash sooner than I think microorganisms are quite safe in the soil and all this, and the extreme temperature do not occur as much as they occur in the air or to a plant exposed to all the elements. So, but it's a one question that is quite important to follow through and see.
Okay, so just to give a heads up to people, I've had just a couple of comments from Shabtai and Paul Beckwith and Claude Butner. There's no questions related with that. If you guys want to ask a question, could you re-enter your request?
Paul said some good thing about along the line that I knew he reviewed a paper that was quite relevant to what I said here, and he might want to say.
Yeah.
I think Art and Dave have questions.
Well, yeah, they were coming down later, so that one of the other, well, let's just go to Art at this point.
Okay, thank you. I guess I do want to say that I was really blown away, Ray, by your presentation. That's just amazing stuff. I was really intrigued by your comment about the ability to measure the amount of methane coming out, and you can measure from aircraft, identify individual animals by the animal. And I'm going, now, isn't that's quite staggering and magnificent? And of course, I immediately thought of using that as a sensor, airborne sensor that could measure methane coming out from individual gas and oil wells. And because it is, I believe, it's underreported. You said 50% underreported. It might even be more for all I know. And then I immediately put my policeman's hat on and said, is this something that could be used to, in fact, use it against the gas and oil industry to get them to be more responsible with regards to their methane leaks? Has there been anybody talking about that?
No, but because like that professor from Carleton said, most of them are not reported, and regrettably, with Twin Otter and all this, the staff that was doing all this work is all retired. So it was a fantastic facility to measure. It would have been a fantastic facility to measure these leakage from oil well and all this. And I'm hoping that there's some talk a bit that NRC might start that plane again for something like this, because it's certainly, it's very, very accurate what the measurement, that estimate that they get, that we're getting. I mean, you're right, we could quantify almost exactly knowing the animal there, we could, the methane emission that we're measuring corresponded pretty well to the emission of the inventory of methane emission. So yeah, and there are many non-reported sources, like what La Flèche waste storage system, they're equivalent to 130,000 dairy cows, for example. None of these were counted in the inventory. Now they probably did something to resolve that problem, but yeah.
Yeah, okay, thank you, excellent talk.
So I have sort of a parallel question before Dave asks his, and that comes from one of your slides that mentioned that farmers should calculate on-farm greenhouse gas emissions. I live in the farm area, and I have no idea how the farmers in this area would have the capability of measuring what was on their farm.
Yeah, that's a good question. The Roland Krobel and the greenhouse gas calculator is very, very good. One can go on the internet and do Holos, HOLOS, and they've given lectures on how to use that calculator, and they've had many farmers online to train to use a farmer. So yeah, they use this calculator to do this, and it's still quite a challenge, you know, but it's progressing, and I think Roland has quite a team. I think he's on today. Quite a team to train people to use that calculator and to
But is that, from a farmer's point of view, is that not a negative impact on their process, on their daily life of having to?
It's a bit of a negative impact, but if you want to try to do your share, and it's at no cost, you can do certain things that, for example, paying somebody to come and put acid in your manure tank, for example. If the government is willing to pay for that, they would feel better. It doesn't affect their yield, and climate change is a big problem for farmers. So I think any real good farmer would be conscious to try to help the situation. That's the way I see it.
It's sort of like adoption of EVs, you know.
Yeah, exactly. Yeah, let's face it, agriculture is not a big emitter compared to the oil and gas car, but we all have to do our share, and if it's for example, it's probably you don't lose nutrient by doing certain things, you know. So certain practices like this are good, and also good for the environment and good for the pocket of the farmer. So
okay, so Dave, you have a couple of questions. Why don't you go ahead and ask them?
Okay, I'll ask them one at a time. The first one is this: how complex is it to measure a gas concentration at surface or near surface at a single point and translate that into an emission rate for something like an oil and gas facility, or as you were saying, say a feedlot?
Yeah, just a single point, you wouldn't give you anything on it. You need to measure, like for example, these lasers that I showed, they have a 100-meter path length. So you put these downwind of a oil well or something like this, it would work pretty well. Or else you can do that balloon idea too, because it integrates over time. At night, it used inversion layer as a cover, and none of the gas escape. There's all kind of ways. If these point sources, though, I think we've done a lot of verification. Like we had point sources in the field, different amount of emission, and using the laser system that I have described, our estimate were almost 100% to what we were emitting, and people put GPS on cows and use this kind of system to measure the emission from individual cows in the field. You know, like they know where they are. They assume they all produce the same amount of emission. So, and they do pretty much. So, based on the feed that they eat, and they're able to come up with the emission of animal in a pasture. So it's not that difficult with the technology that exists to do these measurements. At one point, measurement is not that helpful because wind variation so much that you need a integrated line, you know, like over a distance of maybe 50 to 100 meters to get a good representative measurement downwind of a source, you know.
Mm. Yeah, I guess you have to deal with the three-dimensional diffusion and spread and wind mixing of the gases too.
Yeah.
Must make it extremely complex.
But they have the wind track, like we measure turbulence with the sonic anemometer, and there's a package that does the whole thing for you. That wind track package that I showed, you just enter your measurement and it gives you the answer. And it's been used enormously and it's available on the internet and all this. And I have many colleagues who are using it, and they've tested it, and it works very, very well.
I imagine artificial intelligence may soon
Yeah.
bring about leaps and bounds and improvements. Yeah. Okay, so the second one is you said something about planting trees and lichens growing as a crust on exposed soil, which was fascinating to me. The question is planting trees really a good way to reduce atmospheric CO2 concentrations? And I have another follow-up to that in a moment. That's the first.
It's a very, very slow way in Canada to do it. Eventually it's good, you know, but the things that I showed, for example, the net radiation over coniferous versus grassland was 14 watt per meter square. When I did my presentation, I forgot to show on that slide, there was one little point that said the doubling of CO2 in the atmosphere caused 3.7 watt per meter square difference. Doubling of CO2. And now I have a boreal coniferous forest that affects the net radiation by 14 watt per meter square compared to grassland. So definitely that case is terrible, you know. So in in Canada, it'll be a long time before it's beneficial to. You know, they have a big role and the nice ecosystem and wildlife and all this, but when you look at just the radiative forcing due to radiation balance, this idea of reflect it or store it for carbon is very important, and the storing for carbon is very slow. And like the idea I hear 2 billion tree being idea of planting 2 billion trees, that kind of stuff. It takes a long time to be beneficial, and for a long time it actually causes warming, you know, because the albedo effect is it doesn't reflect the radiation as much as, so it's not the solution that we're looking for decades.
Well, perhaps you and I could pursue that offline at a later date. It's my belief that we've cut down approximately half of the world's forests, but we have emitted into the atmosphere probably in the neighborhood of 100 times more carbon than those forests could possibly ever store if we restored them 100%. Let's put that aside for the moment, because here's my follow-up question, which I think is directly related to what you just said. How long will forests sequester carbon that trees and other plants withdraw from the air? And does that depend on the species and the ecosystems involved? And the reason that I mentioned the latter part is because early in my career, as I was trying to become an ecologist, they gave us measurements that were taken from an experimental forest in the United States and an experimental forest in the Brazilian jungle. And they showed that the fluxes are way different. In the tropics in Brazil, largely what's happening is the carbon's being stored in the living biomass. Once the stuff dies and falls to the forest floor, it very quickly gets turned into dissolved organic carbon, which washes away, which is how you get these black rivers that are famous in the Amazon basin. The carbon isn't staying in the forest, it's being moved out in the rivers. Different story in Canada, I know. That's true. Anyway, so back to the first part of the question, how long will forests sequester carbon, especially when you cut them down every 100 years?
Yeah.
Like,
Yeah.
are we talking momentary in the geologic time?
Oh, definitely monitoring the geologic time. Yeah, 80, 90 year, 100 year. Yeah, you're right.
It's not permanent sequestration at all.
No.
Whereas it's permanently sequestered in the crust when it's in there as oil, gas, and coal.
Yeah, a lot of people would say that you store it in carbon in the soil, but it's true. There's a bit, but it's not any solution to solving the climate change problem.
And so I presume that it does depend on the species and the particular ecosystems. Yeah. Okay.
Yeah.
All right. Here's my last one. It might be a zinger. If Canada expands its population by a factor of 2, in fact, they're planning on more than a factor of 2, will not our agricultural GHGs emissions rise, even if we use technology to lower emissions per animal and per crop hectare?
Yes, they will certainly rise a little bit, but there's so many things we can do also. Like people are talking of feed additive, reduce the methane emission from cattle. There's yeah, definitely they will rise, but agriculture is not the main problem. I would worry more about food shortages across the world, that kind of thing, than and better management and so many things we haven't counted properly, I think, as far as the emission from the agriculture sector. You know, like we put too much emphasis on soil carbon sequestration and not enough on the other thing. You know, and there are all kinds of problems, like things that people 5NR for applying nitrogen in soil, more efficient method. That now they promise by 2030 to reduce the nitrous oxide emission by 30% by better management practices. You know, that's almost covers the 30%. There are a lot of good things we can do without worrying about that, what you asked for, you know. But
okay, great. Thank you very much.
So within your realm, Raymond, who are the most active promoters of many of the different activities that you've been talking about?
Yeah, we're trying to. Yeah, it's a bit difficult to. I don't have active. That's why we try to do videos a little bit, because you know, like there are a lot of Living Lab is doing a lot of good stuff. You know, like in agriculture, to convince farmers have new technique, and they're trying to demonstrate that what they're doing is good, and I think it's a good. But we're not strong on promoting that type of thing. You know, to consumers, for example, we don't do very much. You know, like just I think there's a press release coming out next week about that a little bit, like about albedo and all this, and reflectivity and cooling ourselves. You know, that's sort of cute, but we need to do a lot more promotion. And
okay, and Paul.
Yeah, a couple things. You know, about the planting trees. I think that wildfire control is just as important. I mean, Canada's approach is to, you know, just let a fire that starts in spring burn all summer and go out in the fall when it gets colder, if it's not affecting roads or infrastructure. And you know, the loss of you know, 18 million hectares of trees this last summer, you know, could actually propagate to this summer, because we're, you know, extremely dry, low snow cover out west, etc. And you know, in terms of extracting carbon, I'm just wondering if any of your planes and instrumentation have gone over lakes or coastal regions where there's a lot of upwelling and phytoplankton, because, we're landlubbers, right? We live on 30%, 70% of surface area is the oceans. And if we can get more plankton, we can sequester huge amounts of carbon. And plankton's not going to burn down in a wildfire. But I guess a couple other minor things. I had a question in the chat, do you actually sleep? I mean, you seem to be so prolific with all of your papers and everything. I agree, with the biggest way I think our abrupt climate change is going to hit the world is global food production, especially if we get jet streams locking and getting simultaneous crop failures in crop producing regions. So, do you know anything about food storage in Canada? If we lost most of our crops, could we survive a winter in Canada without having huge imports? And if it's crop producing regions that fail simultaneously globally, those imports won't be there. So how prepared are we for that? Do you know anything about that? And I guess the other big factor is that software for farmers. I'm definitely going to try to play around with it as a non-farmer. Can I apply it to my property if I put in my acreage, the amount covered by grass, gardens, what I'm growing, how many trees are on my property? Can I get some numbers on sources and sinks of carbon, or is there some software for homeowners where you can do the same sort of thing you're talking about for farmers? And I agree, marketing, we can do wonderful things, but if it doesn't get out to the public and farmers, then, we're kind of very frustrated because the tools are there, but how do we get communication to people? And I think the federal government has completely dropped the ball on communicating, why is there a carbon tax? Why are these things necessary in Canada? They never talk about it. They just get attacked from the right all the time, and yet they don't ever give the reason or say how bad climate change is. It's not just the federal government, it's the provinces, it's everybody. It's a communication issue about climate in general. So there's a lot of questions. So, just if you can comment on what you think, especially the food storage. I mean,
I'll thank you, Paul. I'll comment a bit on each because the food storage is not my expertise that much. The interface, for example, you were mentioning at first, our system are not very good at coastal. So we've flown over lake, but not interface like this. We're not very good at our system are not very good to quantify, exchange. Mind you, people could have small tower-based system, but it's quite tough. The interface are very tough to. Food storage, I know very little, except that we produce a lot of food and we're exporting a lot. So I think we have quite a buffer for ourselves. But it's something, it's the thing that on a worldwide basis is the thing that I expect will be the biggest thing. As far as software, OLOS is very good, but it's not good as at the farm level. But maybe Roland will be encouraged to do that. Like we had the model farm project, and we got $40 million from the government to develop OLOS, and about around 2008, and it's still like we at least with this we gave a lot of money to the various the dairy sector, the pork sector, the different sectors to familiarize them with climate change, and we focus more on these sectors as far as OLOS and rather soil conservation group rather than focusing on the small at a small homeowner level. As far as the carbon footprint, you're right. It's, to me, farmers, we don't do a very good advertisement on what could be done with carbon tax, because I think things like having a consultant come and put something like acid in your manure tank, and that clearly shows that you've reduced your emission by almost more than your foreign produce. Like so. There are a lot of things we can do much better than we're doing.
Yeah. Thank you. Anyway, great talk.
Okay, well, that is going to be the wrap up of the Q&A session. I've been asked to sort of remind people that next week we are having our presentation on Thursday afternoon, not on Wednesday afternoon. So just change your little notes in your calendars, and we'll see you next week. And Jean, you're here to say a few good words, and then we close off.
Thank you, Phil.
All right. Thank you, Phil. And Raymond, thank you very, very much for an absolutely phenomenal presentation that you gave. It's wonderful to see the work that you have done through your career and incredible results that you were getting. And I think the application in so many other sectors, not just in the agricultural sector, for your ability to measure CO2 on the fly, literally, is just an absolutely wonderful contribution to some of the problems that we are facing as a society. So thank you for this wonderful presentation. Really highlighted what we can do as a group if we put our brains together. For those of you who are still here, I would like to say, please go to our website at canadiancore.com. And if you sign up for the Stay Informed section, you will receive the invitation to look at this particular video and all the other videos that we have produced over the last 2-3 years. And there's a wealth of information in those videos, and the work and presentations that have been done have just been incredible. And Raymond, you have produced one of the best ones that we've had in a long time. So thank you so much for that. And also, if you're interested in getting more information about CACOR, the Canadian Association for the Club of Rome, please look at the website, see some information, and join us. It's not an expensive proposition, and you'll get access to a lot of information and a lot of conversations that go on with people of like minds for you. So with that, Raymond, thank you so much for a great presentation.
Thank you, G. It was a pleasure.